Right now, a fleet of NASA spacecraft are turning their attention to an unusual object speeding through our solar system.
Something astonishing has unfolded as 3I Atlas hugged the sun's influence in a way that seemed, at first glance, impossible. That interstellar wanderer, sliding into our solar system on a hyperbolic trajectory, has just executed a cosmic act that challenges expectations about comets, interstellar bodies, and how they respond to solar heating. Before we start, smash the like and subscribe buttons for more updates. 3I Atlas, the third confirmed interstellar object ever observed.
According to astronomers, 3I Atlas has all kinds of surprises. We've only seen a handful of blurry shots that there's the unusual chemical signatures. It's producing way more nickel than iron, and scientists don't really know why.
Carries a name that signals both discovery and mystery. It was detected by the Atlas survey system, and the 3I marks it as the third known visitor from beyond our solar domain.
3I Atlas was discovered on July 1st by the NASA-funded Atlas survey.
Its path is not a gentle ellipse, but a hyperbola. This is not a body captured into orbit, but one that flings itself through, never to return. As it approaches perihelion, it draws ever closer to the sun. And that moment of closest approach promises to be the stage for something extraordinary. What makes the recent behavior of 3I Atlas so extraordinary is that it appears to have activated in a way no other comet has quite before. As solar radiation intensifies, comets typically begin to sublimate. Ices transform directly into gas, carrying dust and volatiles away to form a fuzzy coma and eventually a tail. But 3I Atlas has revealed a coma overwhelmingly dominated by carbon dioxide, with water vapor, carbon monoxide, and other volatiles playing secondary roles. Infrared spectroscopy from JWST, the James Webb Space Telescope, captured this dramatic dominance. The mixing ratio of CO2 to H2O in the coma is an outlier, far greater than what typical solar system comets display, suggesting that 3I/Atlas's S nucleus is intrinsically rich in CO2 or has structural features that suppress water emission relative to CO2 sublimation. As it draws nearer to the sun, the comet doesn't simply emit in a symmetric halo. There is evidence of enhanced outgassing in the sunward direction, a plume of dust and gas preferentially pushed toward the sunlight side. That is surprising because normally the pressure of sunlight pushes material away from the sun, forming a tail in the anti-solar direction. Here, what's being seen is an anisotropic sublimation front, an asymmetric release of material, stronger in the sunlit hemisphere. This manifests as a sun-facing feature, a plume rather than a typical tail, and betrays unique thermophysical properties of the nucleus, perhaps rooted in composition, surface layering, or insulating materials. Even more confounding is a phenomenon called an anti-tail, an apparent tail that seems to stretch toward the sun. But this is not merely deceptive geometry. In the case of 3I Atlas, the anti-tail may stem from the asymmetric sublimation and survival of ice grains oriented in the direction of the sun. Because in the sunward direction, the sublimation mass flux is stronger, grains ejected toward the sun may survive longer, form extended structures, and thus create the visual effect of a tail pointing inward. The physics of sublimation anisotropy and grain survival can produce such anti-tails not as illusions, but as real structural features in the coma environment. Perhaps most dramatic was the signal that 3I Atlas switched on suddenly during its approach. Some of its volatile releases are rising in a superlinear fashion, not in a smooth, gradual heating curve, but in a threshold-driven burst as certain temperature thresholds are crossed. Observers noted that as the comet warms, emissions of cyanide CN and atomic nickel vapor surge in a manner not simply tied to solar flux. The appearance of these species, and their dramatic increase at specific heliocentric distances, suggests that some process was latent until a critical heating point, at which point dramatic outgassing erupted. That behavior, basically turning on more violently than classical comets, is what gives the impression that 3I Atlas has done something impossible. It has broken from the norms of sublimation physics seen in comets from within our system. As it approaches perihelion, 3I Atlas will reach its closest distance to the sun around the 29th of October 2025 at about 1.36 astronomical units, positioned between Earth's orbit and that of Mars. At that point, its velocity relative to the Sun will be maximal. That's the moment when the Sun's heat and radiation pressure act most strongly, and when the comet's internal dynamics face the greatest stress. This event, 3I Atlas, Doing the Impossible, is not only about extraordinary emissions, but about how an interstellar nucleus reacts under solar forcing in real time. For comets formed within the solar system, models of layering, volatile stratification, and erosion dynamics are grounded by decades of observation. But 3I Atlas is not bound by those histories. It carries the memory of a different birthplace, possibly irradiated or altered in unique environments. Its behavior could be dictated by exotic ice mixtures, unusual porosity, internal layering of unexpected chemicals, or structural brittleness under thermal stress. The fact that CO2 dominates and water is suppressed relative to expectations suggests that the nucleus's thermal conductivity, porosity, or insulative layering may be extreme. It means heat may be channeled in ways that trigger steep gradients, causing sudden outbursts when thresholds are crossed rather than smooth gradients. The result is the triggering of switch-like behavior and volatile release that classical comet models do not normally predict. Polarimetric observations add another layer of mystery. 3I Atlas exhibits an extremely deep negative polarization at small phase angles, values and behavior not matched in typical comets or asteroids. That degree of negative polarization at low phase angles suggests that the scattering and reflective behavior of dust and ice grains in its coma are unusual. The light may be strongly oriented in the Sun-Comet observer plane under specific geometries, indicating unique combinations of grain size distribution, composition, porosity, and internal structure. In other words, not only is the gas release unusual, but the microscopic behavior of dust and ice grains is exotic compared to known comets. In tandem, photometry and careful brightness monitoring show that throughout its inbound route, 3I Atlas has brightened substantially, not in a gentle linear way, but in fits and surges that correlate with heating thresholds. That suggests that internal stresses, pressure buildup, and crack propagation may be occurring, fracturing icy layers or opening vents in ways not seen in ordinary comets, perhaps because of unknown internal layering or high levels of volatile pressure. As it approaches perihelion, such behavior could intensify, especially as thermal gradients steepen and the Sun's influence overwhelms internal cohesion. Another astonishing wrinkle is that this comet began releasing water vapor and showing signs of activity when it was still far from the Sun, at distances too cold for classical water-ice sublimation under normal expectations. That early leakage implies that volatile ices of species more volatile than water like CO2 or CO or other exotic species are present closer to the surface, and perhaps overlying materials limit thermal conduction, so even moderate solar heating triggers unexpected early outgassing. In effect, its pre-perihelion behavior is inconsistent with simple comet models calibrated on solar system comets. This is the cosmic drama. An interstellar body behaving more wildly, more unpredictably, more threshold-driven than anything seen before? As it nears the Sun, 3I Atlas is not simply glowing and sprouting a tail, it is transforming, breathing, reacting to a heating environment in real time, revealing internal secrets. The impossible here is that it is crossing boundaries between comet behavior categories, surpassing expectations from solar system analogs. Because it is interstellar, the stakes are higher. If this behavior reflects materials, structures, or processes alien to our familiar comets, it hints at how bodies in other stellar systems evolve. The richness of CO2, the suppressed water, the intense threshold emissions, the asymmetric plume, the sunward features and anti-tail, and the exotic polarization all converge into a signature unlike anything cataloged. This suggests that interstellar bodies may not simply be comets like ours, but from far away. They may be fundamentally different in composition and structure. Observationally, this event is a rare real-time experiment. As 3I Atlas crosses perihelion, instruments on Earth in orbit and aboard spacecraft will capture its evolving emissions, spectral signatures, dust spread, plasma interaction, and morphological changes. The interplay between solar radiation, sublimation, dust release, ion tails, and magnetic draping will play out dynamically. One might see sudden fragmentation, jetting, asymmetric outbursts, or rapid changes in tail morphology. For solar system science, witnessing this is like catching a probe into alien territory. It challenges the assumption that cometary models developed from Halley, Encke, or typical comets apply universally. It forces us to consider new thermophysical parameters, new layering arrangements, and new volatile chemistry. It may demand rethinking of how ices survive in different environments, how radiation processing influences volatile reservoirs, and how interior thermal insulation can modify outgassing. If 3I Atlas truly switches behavior at temperature thresholds, that hints at latent volatile reserves frozen at deeper layers, reservoirs that only activate when heating crosses a boundary. That tells us something profound. This comet may have preserved volatiles in more pristine form than many solar system comets, which may have lost much of their exotic volatile species over billions of years. In that sense, 3I Atlas may be a more pristine sample from a distant origin, offering clues to volatile inventories of regions beyond our formative neighborhood. This event forces astrophysicists to confront whether interstellar comets should be categorized by distinct thermochemical classes. It raises the question, how many comet types exist across galactic systems, and how representative are the comets we've studied in our own system? Maybe comets around other stars are richer in CO2 or exotic gases, and what we've seen in our solar system is only a narrow subset of possibilities. The impact of this impossible behavior also extends to planning future missions. If interstellar comets can switch on in unexpected ways, then missions designed to rendezvous or fly by them need to anticipate volatile surges, unpredictable jetting, and structural instability. The models for trajectory planning, shielding, and instrumentation must account for more exotic and abrupt activity. Furthermore, this phenomenon suggests new observational strategies. Comets entering from interstellar space may need to be monitored not just for brightness, but for spectral changes and threshold signatures. Instead of expecting smooth exponential brightening, astronomers must watch for sudden onset points where volatile bursts begin. That means more frequent spectral snapshots, polarization monitoring, and high-cadence observations as they approach critical heliocentric distances. In the grand tapestry, the moment 3I Atlas did the impossible is a turning point. It transformed from a passive visitor into an active, unpredictable participant in solar dynamics. It became a real-time laboratory for studying how exotic bodies respond to solar heating, how volatile layering behaves under stress, how dust and gas flow under anisotropic control, and how material properties established in far-off star systems manifest under a star's embrace. The cosmic implication is profound. There is more diversity in cometary behavior than previously assumed. We now have witnessed an interstellar object that acts like no comet we've studied before. And as it slides through perihelion, it will reveal more of its secrets, chemistry, dynamics, morphology, over the coming weeks. Its journey is a message. The solar neighborhood, though familiar, may now host visitors whose internal rules differ from our expectations. What remains is to watch closely, to capture spectra, to map dust and gas flows, to monitor polarization, to compare models, and to allow this object to teach us not about what we already knew, but about what we didn't even imagine could happen near a star. The sun's fierce radiance has begun to pry open secrets within 3I Atlas, and what it has revealed is nothing short of transformative for how we think about objects from beyond our cosmic neighborhood. Far from simply lighting up, the comet is unfolding into a being of active chemistry, shifting morphology, and volatile alchemy. Behaviors that demand we rethink the boundary between familiar and unknown in comet science. A striking revelation is the detection of water far earlier and more forcefully than expected. At nearly 3.5 astronomical units from the Sun, distances where water ice sublimation is typically negligible, strong ultraviolet emission of hydroxyl radicals, OH, has been observed. That emission is the smoking gun for water breaking apart in UV radiation. From that, scientists estimated a water production rate of roughly 40 kilograms per second. This level of activity so far from the Sun challenges conventional wisdom. Either water is more readily liberated on 3I Atlas than models allow, or additional processes amplify the conversion of ice to vapor. That water release also requires a surprisingly large active fraction on the nucleus. If the nucleus is somewhat large, then more than a fifth of its surface must be actively venting material, far more extensive activity than typically seen in solar system comets at comparable distances. This suggests that the comet's surface or near-surface layers are unusually permeable or fractured, perhaps environmentally preconditioned by prolonged cosmic exposure before arriving in our system. The Webb Space Telescope's infrared observations further expand the surprise. Its near-infrared spectroscopy reveals that the comet's coma is overwhelmingly dominated by carbon dioxide gas, with minor contributions from water, carbon monoxide, and other species. The measured CO2 to H2O mixing ratio is about 8, meaning CO2 is 8 times more abundant than water in the escaping gas. That is among the highest such ratios ever recorded in a comet. It suggests that 3Y Atlas may have formed in an environment where CO2 ice was abundant, or that its internal structure strongly suppresses water release while permitting CO2 to flow freer. Coupled with this is the asymmetric outgassing signaled by the observations. Gas ejection is stronger toward the sun-facing hemisphere rather than being distributed evenly. That is unusual because solar radiation pressure normally pushes ejecta away from the sun. In this case, the geometry of heating and gas flow seems to favor a concentrated directional plume in the sunward direction. That asymmetry not only alters the shape of the coma, but could impose torque or force on the nucleus, potentially altering its spin or orientation. Polarimetry adds yet another dimension to the mystery. Measurements at small phase angles show a deeply negative polarization branch in the scattered light, reaching minima unseen in typical comets or asteroids. The inversion angle, the point at which polarization switches sign, comes in around 17 degrees, and the slope of the negative polarization branch is unusually steep. These properties strongly imply that the dust and ice grains in the coma have unique size distributions, porosities, or internal structures, not just dust like solar comets, but dust shaped by unknown histories. The microscopic surface structure of particles, their compaction or fluffiness, and how light scatters within them may differ profoundly from anything Earth's comets have given us. Spectroscopic work in the optical and near-infrared places constraints on the composition of dust and ice grains in the coma. The spectrum shows a red slope across visible wavelengths, similar to some dark D-type asteroids, transitioning into a flatter slope in the near-infrared. Modeling these features suggests that the coma could be a mixture of refractory, non-volatile material akin to meteorite analogs and sizable grains of water ice. In one interpretation, a rough mix of approximately 70% of a Tagish Lake meteorite analog to approximately 30% water ice grains reproduces the observed continuum and the broad absorption feature near 2 microns. That implies there are large ice grains present, not just fine vaporized molecules contributing to the coma's makeup and behavior. Because of these large icy grains, 3I Atlas may carry an extended source of water, fragments or grains that sublimate gradually over time, rather than releasing water exclusively at the nucleus surface. Those grains, once lofted into the coma, can act as secondary emitters, sustaining water vapor release even when insolation reaching the nucleus itself is modest. That mechanism helps reconcile why water is being liberated at distances where direct sublimation is inefficient. The nucleus itself remains unresolved, cloaked by the bright coma, but Hubble's imagery constrains its diameter to somewhere between hundreds of meters and several kilometers. Upper limits perhaps as large as 5.6 kilometers, though smaller values cannot be ruled out. The brightness and spatial fuzziness thwart direct measurement. Trajectory and orbital dynamics underscore how extraordinary this interstellar visitor is. Its orbital eccentricity, well above 1, cements its origin beyond the Sun's gravitational domain. Its hyperbolic excess speed is exceptionally high, on the order of tens of kilometers per second beyond what gravitational capture would allow, making it one of the fastest interstellar objects ever tracked. Its inclination and orbit orientation amplify the strangeness. 3I Atlas travels on a retrograde path nearly aligned with the solar system's ecliptic plane, within a few degrees. That near alignment is unexpected for an interstellar object, which would more typically approach from a random orientation. That it arrived in such alignment hints at either a bias in detection or deeper underlying structure in how interstellar debris is distributed. What 3I Atlas did near the Sun is a dramatic demonstration that its interior and surface are not passive. As solar heat penetrates, it is likely encountering layers of volatile ices, refractory crusts, fractures, and possibly supervolatile reservoirs. At critical junctures, latent heat triggers rapid sublimation, fracturing of ice, or blowout of dust, turning on parts of the nucleus that had remained dormant. That thermophysical switching suggests complexity, layered insulation, knockout vents, subsurface cavities, or zones of volatile trapping. It is not just a homogeneous ice ball, but a differentiated, perhaps evolved body. As 3I Atlas draws closer to perihelion, the thermal gradient steepens sharply. The side facing the Sun warms rapidly while the interior lags. That mismatch can introduce stresses. Cracks can propagate, volatile pressurization can build, and structural failure or outbursts could ensue. The comet may shift in brightness nonlinearly, erupt new jets, or shed chunks of material. Because its volatile budget is rich and exotic, the response may be more sudden or extreme than solar system comets typically display. Because CO2 is more volatile, that is, it sublimates at lower temperatures than water, it may dominate outgassing earlier and more forcefully. That dominance may also act as a thermal throttle. The release of CO2 could absorb latent heat and shield deeper layers temporarily from heating, modulating the internal temperature rise. Thus, as water sublimation becomes possible, its release may lag or be partially suppressed, consistent with the observed low water presence despite strong CO2 flows. One can imagine jets of material opening and closing like valves, responding to thermal fractures. As cracks open, volatiles rush out, possibly dragging dust and chunks of icy material with them. Once a jet depletes its local reservoir, the crack may seal or cool, and activity quiets until heating reopens it. The comet may then cycle through phases of quiet and eruption as it rotates under solar forcing. Given the asymmetric outgassing, the net forces on the body may apply torques, altering the nucleus spin state. Over time, the spin axis, rotation period, or orientation might change. That dynamical evolution can feed back on the heating pattern by changing which hemisphere receives more sunlight or shadow, and thereby influence which vents activate next. In effect, the object can enter a feedback loop of heating, outgassing, spin change, and reconfiguration. Close to perihelion, the physical stresses intensify. Tidal influences, though relatively minor at distances beyond the Sun's Roche limit, combined with internal thermal pressure, may lead to fragmentation or mass shedding. The nucleus could fracture partially, exposing fresh volatile-rich surfaces. If cracks open from within, fresh material previously insulated by crust can suddenly be exposed, triggering a sudden surge in gas. The comet might shed boulders or even split, altering its morphology. As it continues on its inbound trajectory, the comet's tail structure may evolve dynamically. Ion tails, driven by the solar wind, may form and reorient rapidly. Dust tails, influenced by radiation pressure and grain size distribution, may show structures, dust jets, fan features, or striae if fragmentation events occur. The interaction between dust, gas, and the solar wind's magnetic field forming a plasma envelope or magnetotail may produce complex signatures, such as kinks, disconnections, or twisting tail segments. Because 3I Atlas already displays unusual chemistry CO2 dominance, suppressed water, the gas-dust coupling dynamics may differ from normal comets. Dust may be more weakly bound by gas drag, grains may be larger, or ice grains may sublime slowly, influencing tail morphology and dynamics in novel ways. At the heliocentric distances near perihelion, the solar ultraviolet flux and solar wind pressure are much stronger, so ionization of gas and plasma interactions become more intense. One may observe enhanced emission lines, plasma jets, interactions with the Sun's magnetic field, and possibly bow shocks or magnetically mediated features. This is not just a passive comet, but an active plasma source carving a temporary disturbance in the near-Sun environment. Another dimension is comparative chemistry. During these intense solar interactions, rare species such as nickel atoms, atomic oxygen, sulfur compounds, radicals like CN or C2, and complex organics may be liberated. The sudden appearance of nickel vapor, for instance, implies deeply buried metallic inclusions or refractory minerals being vaporized by high heating. That kind of detection suggests that 3I Atlas may harbor materials rarely preserved in typical comets due to long-term solar processing. Such metal atoms in the coma speak to primordial mixing or exotic initial conditions. The fact that 3I Atlas already emitted significant water and other species so far from the Sun also implies that the activation zone for volatiles is broader than expected, perhaps beginning in deep space before significant solar heating. In that sense, the comet may have been preheated by a previous close stellar passage or cosmic heating that made volatiles more responsive to sunlight. Its internal structure may be pervasively fissured, with pathways for gas to leak even at low insolation. The detection of extended icy grains and the suggestion of an extended coma source means that the comet's gas output may not directly mirror instantaneous heating at the nucleus. Instead, there may be a time delay or smoothing effect. Grains launched earlier will slowly sublimate later, contributing to gas output even after heating subsides. That temporal decoupling between heating and gas release can complicate the brightness curve, making it more irregular with memory of prior heating. Because its composition is so high in CO2 relative to water, 3I Atlas might resemble bodies formed near a CO2 ice line in its origin star system. That ice line marks the region in a protoplanetary disk where carbon dioxide transitions from gas to solid. If the comet formed near that boundary, it might have accreted and preserved large CO2 reservoirs. Alternatively, cosmic irradiation or chemical processing could have locked extra CO2 in clathrates or trapped phases less accessible in solar system comets. The suppressed water signature then could owe to a thick insulating dust mantle or refractory crust that blocks heat conduction, preventing deep heating and water sublimation, while CO2 more volatile and located nearer the surface can still escape. One must also consider evolutionary histories. If 3I Atlas has journeyed for eons through interstellar space, it may have endured cosmic rays, micrometeoroid bombardment, radiation processing, thermal cycling, and abrasion. Those processes can alter the structure of the outer layers, compacting or annealing the surface, creating a refractory shell or modifying porosity. The interior might remain pristine, but the outer layers can act as a thermal barrier, dictating how heat penetrates and thus controlling volatile release patterns. Moreover, the fact that water appears at large distances suggests that some volatile reservoirs may be shallow, close to the surface, or embedded in large grains. That is atypical compared to solar system comets, where water ice tends to be deeper. Perhaps the formation environment or post-ejection processes allowed volatile migration closer to the surface. Another twist: the orbital origin direction is intriguing. 3I Atlas arrived from a trajectory nearly opposite to what one might expect based on solar apex motion. That suggests that the stream of interstellar debris is more isotropic, or that gravitational perturbations have scattered objects into unexpected paths. The detection of 3I Atlas along the ecliptic plane suggests that many such objects might traverse through the planetary plane unseen until they brighten. The fact that one turned on in such a dramatic way near the Sun gives hope for discovering more such comets in the future, but also caution. Their behavior may be far more unpredictable than classical comets. The phenomenon of turning on with threshold behavior is thus not a quirk, but may be a window into how interstellar bodies accumulate volatiles, preserve them in metastable form, and release them under stress. It suggests that many interstellar comets might lurk dark, undetectable until they cross a thermal threshold where sudden sweeping volatile release lights them up. If that is the rule rather than the exception, our current sample of interstellar objects, only 3 to date, may be heavily biased. Because 3I Atlas is the brightest and largest interstellar object yet observed, its behavior might set a new benchmark. Its size and brightness enable more detailed study, spectroscopy, polarimetry, imaging, temporal monitoring than its predecessors. That means the impossible behavior we now see may not be unique. It may be that prior interstellar visitors were simply too faint to reveal such detail. What seemed anomalous now may be commonplace among objects in distant systems. As it closes in, the interplay between solar heating, gas release, dust dynamics, and nucleus structure will accelerate. We may see the emergence of jets, fragmentation events, sudden brightness surges, complex tail morphology, or changes in polarization or spectral lines. The comet's behavior will likely diverge increasingly from conventional expectations, revealing more of its internal architecture and volatile inventory. By the time it reaches perihelion, 3I Atlas will have undergone the most intense heating and stress of its journey through our inner solar system. Its behavior just before and after perihelion may include peak volatile release, maximum dust ejection, structural changes, and morphological complications. Those near-Sun moments may even push it to fragment or reconfigure significantly. While this narrative plays out across days and weeks of observation, the implications ripple beyond this one comet. The impossible act is not a singular aberration, it is an invitation to expand our models. Cometary physics, formation history, volatile reservoirs, internal structure models, thermal response laws, fracture mechanics, dust-gas coupling, and plasma interactions may all need retuning when confronted with interstellar diversity. The unexpected interplay of CO2, water, asymmetric jets, polarimetry, and kinetics reveals that 3I Atlas is not a comet by the book. It is a messenger of alternate rules. It teaches that cosmic travelers carry legacies of their birth environments, radiation, chemistry, temperature regimes, all preserved in ice and dust and waiting to reveal themselves under stellar glare. This moment of doing the impossible is not just the comet's act, but ours. A moment forcing human science to stretch, adapt, and rethink. In the coming days, as solar heating intensifies and observations capture shifting patterns, 3I Atlas will continue to defy and instruct, becoming a Rosetta Stone not for Earth's comets but for comets born in alien disks, showing us that what we call normal is only one chapter in a vaster cosmic diversity. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on 3I Atlas doing the impossible near the Sun? What do you expect next? We want to hear from you. Thank you for watching, and see you next time.